Welcome everyone. Today we'll be solving a very fun polynomial question. We're given a polynomial in this form, where as you can see we have two unknown coefficients p and q, and we're also given the fact that it has two double roots, or basically in its factorization for some roots a and b that they are doubled. And the question is to find the sum of these unknown coefficients p and q. So I highly recommend you give this problem a try for yourself before I reveal the key to solving it. To solve this problem, I must make you familiar with the concept of a symmetric sum of the roots of a polynomial, and it's also known as Vieta's formulas. So I'm going to give you a quick definition and some example on this cubic polynomial. So we call the k-symmetric sum of the roots as the sum of the product of the roots combined k at a time. So that was quite a difficult definition, but I hope that it makes sense with these examples right here on board. So the first symmetric sum, we write it as sub 1, is going to be the sum of the product of the roots combined one at a time. Combining the roots one at a time means that we are just summing them up individually as such. Now the second symmetric sum is a bit more interesting because we're combining the roots 2 at a time and taking that product. So it is going to look like this. And there's no repetitions in our combinations 2. And the third symmetric sum, where we're combining the roots 3 at a time, and because there are only 3 of them in a cubic, it is just going to equal to the product of the roots. So as you can see, the symmetric sum ranges from the first one to the symmetric sum of the degree of the polynomial. And there is a general formula to evaluate this symmetric sum just using the coefficients of a polynomial. And it goes like this. Now, unfortunately, the proof is a bit too long for this video, but I can make a separate video proving this if enough comments tell me to do so. So if you'd like to see it, please tell me down below. So now that we established these definitions, we can proceed to using these symmetric sums and using the formula to evaluate the symmetric sum in our problem. Now, if we write out all of the symmetric sums of the roots of this polynomial, or in terms of a and b, and evaluate them, we will notice something quite interesting. So let us do that. The first symmetric sum is going to be the sum of all of these roots in the polynomial's factorization. So although there are only 2 unique roots, it doesn't mean that there isn't 4 of them in the factorization. That's what the fundamental theorem of algebra, in fact, tells us. So there must be 4 of these right here, and this is going to just equal 2a plus 2b. And we can evaluate it by the formula I showed you. It is going to be the coefficient of this cubic term divided by the coefficient of the quartic term, and with a switch sign. So it is going to equal 16. Okay, now let's get on to the second sum. We're going to combine each of these a's and b's twice. We're going to have one a squared and one b squared term, and then there's going to be 4 ab terms as such. And we can also evaluate it by the formula. So this square coefficient by the quartic coefficient to get 94. All right, now for the third symmetric sum, we combine these roots 3 at a time. And you will see that we will get 2 a squared b terms and also 2 b squared a terms. Now we can again evaluate this, but it will now be in terms of our unknown coefficient here. It is going to equal to negative p. All right, and the fourth symmetric sum, it is just the product of the roots. So a squared b squared is going to equal q. And as you can see, we have q and p right here in terms of a and b. So in fact, from this, we derive that q plus p, well, it's going to be the value of q and then minus the value of p, because the minus the value of minus p right here. Sorry, because right here we have it expressed in terms of a and b. So this is going to equal our value q plus p to a squared b squared minus 2a squared b minus 2b squared a. And we can find this value because we have a and b terms in the first and second symmetric sums, which we know the value of. To proceed, we can use a bit of clever factorizations and some manipulation. So notice first that q plus p can be factored as the product of a and b squared minus 2 times ab times a plus b. So really all we need to find q plus p is the product of a and b and the sum of a and b. And we can get that because we know the value of the first and second symmetric sum. So from the first one, it should be quite obvious that S1 is equal to twice a plus b, and we know its value, which is 16. So a plus b, their sum of the roots, is equal to 8. Well, technically half the sum. The sum of the unique roots is equal to 8. Now, the second one, we can also use that to find our product of the roots. Notice we can factorize the second symmetric sum as a plus b squared, which is going to yield what? A plus a squared plus b squared plus 2ab, right? And we also have an additional 2ab term. That is going to equal 94. We know that a plus b is 8, and this squared is 64. So then we get that 2ab is equal to 94 minus 64, which is just 30. And so the product of a and b is equal to half of 30, which is 15. And that is it. We are basically done. Because we know the value of the product and sum of a and b, we can evaluate q plus p. We get that q plus p is equal to, as we factored it here, it's going to be 15 squared minus 2 times 15, minus 2 times 15, and then times 8. And this should be really easy to solve even without the calculator. This is equal to 15 squared minus 16 times 15, which is of course minus 15 if we factor out the 15. And that is going to be our answer to the question from the beginning. P plus Q, the sum of these unknown coefficients, is equal to minus 15. So that is it for today's video. I hope you learned something new about the symmetric sum, also called the Vieta's formulas. And this is a very interesting result of polynomials and what makes polynomials so easy to work with as well in some other applications, not just competition settings. So yeah, thank you for watching. I will see you in the next one.